This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
The rest of you haven't put your hand up because you just don't want to put your hand up, or you're embarrassed, or does it mean that you really don't know and have not gone through Maxwell's equations and, transmission lines and RF systems? Remember, this is supposed to be interactive. You're supposed to say, no, we don't know, Stan, you're going to go slow for us, or yeah, we've done it 100 times, don't waste my time. I've done it 1,000 times before, I know it like the back of my hand. Stan, give us the hardest stuff that you got because we want to learn the most. What can you give me? Sorry? You don't know Maxwell's equations? Okay. All right, so what we'll do is I'll go slowly. I'll try to go through the whole process. Now, please, if there's things that you don't understand, let me know. And what I'll do is also, rather than just the lecture notes, I'll also try to get some other information, handouts and the like that I can actually provide to you so that you can actually become familiar with the content. And remember, this is absolutely critical content. And I can't emphasize enough that you're all graduating next year and you haven't done transmission lines, and Maxwell's equations before, because I can tell you with certainty that if I was interviewing you in the next few months, I'd be asking you that, and the interview would stop pretty quickly. Anyway, all right, cool. All right, so what's this course about? What's the first part of this course? Can everyone read this? I apologize, I didn't think it was going to be this bad it looks great on it looks good enough to me on the screen, but can you see it? Bit small, okay. Now, can I do this? No, still too small. Okay, let me do this, right? Now, it's pretty pathetic drawing. It's supposed to be almost cartoonish, right? But what I'm trying to, half day of the course, what I'm trying to teach you all about is RF systems. And then the question's going to be from all of you, why do I want to learn about RF systems? Okay. And the reason is quite simple, right? Every time you grab one of these things and you put it next to your ear, or you're doing, what is it, WeChat? Is that what everyone uses, WeChat? Yeah. So when you're doing WeChat, there's a whole bunch of things that are happening in order to enable you with that, in order to facilitate you being able to communicate with the base station and then the base station across to the rest of the world. Now, why RF systems? Well, at the moment, you guys, much younger guys, and when I say guys, I mean in colloquial sense, that means guys and girls, right? So when I say guys, it's guys and girls. When you do this, you don't like in my age where you have to plug in a wire or you have to be behind a computer in order to be able to communicate, right? So you're all used to, the era where all communication is wirelessly based, which means that you are at one location and you're transmitting information to some other location, and you're doing that with the benefit of not needing to be connected up by a physical piece of wire or with a physical piece of optical fibre, right? Now, in order to do that, there's a lot of things that are happening in the background, even at the RF layer or at the signal layer, or the physical, what I should call the physical layer, in order to facilitate that. And what the first part of the course is going to focus on is on that, specifically that physical layer, and even within that physical layer, more specifically, the area interface. Okay. And essentially what happens is every time you transmit a bit of information, which is, mind you, is given your voice, it's digitized and transmitted as bits. Or even in my age, when we would be an analog signal, so you've seen digitized versions of the one's voice. what's actually happening is you've got a whole bunch of the electronics in the transmitter, right? And then, of course, in the receiver. That, which is usually starts off in the digital domain, right? So you therefore, you know, if you're doing WeChat, you're actually generating digital data. That digital data is then sent to the baseband, right? And the baseband actually converts that into an analog signal, usually a low frequency analog signal. And then that analog signal is sent to the RF interface, which then operates at a higher frequency, which then is used in order to, it is amplified and then is used to modulate or actually power an RF antenna. Right? The RF antenna has some very interesting properties where it's able to convert that interesting signal, which conveys your WeChat conversation, into an RF signal, so that actually leaves the antenna. You can think of it as generating waves or photons, which are then transmitted across the air, potentially many kilometres away, in order to be received and go through the reverse process on the receiver. Right? Now, so what we'll do as part of this is we'll try to understand also how antennas radiate. We'll talk about EM radiation. Of course, we'll talk about noise. Why is noise important? I believe in that, I'm old, remember? Sure, and it'll affect the signal to noise ratio. Yeah, so it'll cause a degradation, that's right, it'll cause a degradation. You call it distortion, I don't want to call it distortion, but it's distortion something else, and we'll talk about distortion. But what it does is it affects the signal, it degrades the signal, and what essentially happens is by degrading that signal, your signal to noise ratio decreases, and as a consequence of that degradation, that decrease in signal to noise ratio, the number of bits that you can actually transfer across that channel reliably without error decreases. Right, so we will talk about thermal noise, we'll talk about the shot noise, we'll talk about distortion, which is what happens when you've got, how do you call it, nonlinearities in your power amplifiers and that, which we will talk about. And then we'll also go through a little bit on transmission lines. Now, question. Regarding noise, is there always, can we have a system with no noise? Why not? Yeah, of course, we'll say, yeah, no noise, but you always have that noise. Suppose I was pointing to something, would I get noise? So for example, if I point, let me ask a different question. If I was pointing out to the universe, right, into deep space, I would get some amount of noise. And if I was pointing towards the sun, I'd get a different amount of noise. Which one would we expect to have more noise? And why? Sun, correct? Yes? Radiation, which does what? Sure. So what will happen is there's essentially what it does, that electromagnetic radiation is first A, you can pick it up, but B, what it does is it makes the electrons in your wires or in your antenna jiggle around, right? And what happens is these electrons, if you go through, remember you said this in mechanics, some of them are going very fast, some of them are going very slow, but the ones that are going very fast smash into the part of the lattice of your wires and actually generates noise. So noise is something fundamental that we can't really avoid, but it's something that we have to deal with. Anyway, so this is why we're doing, we're going to go through the next, I guess, what is it, 13 weeks of pain? Is it 13 weeks? I think it's something like that. So this is the reason why we're going through all this. It's to actually be able to design, understand, specify, and design these systems, and be able to do it both from an RF perspective actually understand radiation, EM radiation, but also understand the electronics, design the electronics and specify the electronics. All right, so it's super exciting stuff. Super, super exciting stuff. You should be glad that you've chosen this subject. Okay, so what I'll do, and this is just an overview of the, I apologise, let me go full screen, and I'll give you all the lecture notes. So don't stress. So the other thing I want you is don't stress if you didn't capture something on the lectures. I'll put the lectures up so you can always have them. And what I'll also try to do is at the end of each lecture or the start of the next lecture, also go a quick review over the stuff that I went through the last time. So that way it just always helps you contextualise what we've learnt. Okay, I apologise, let me just go to full screen again. Okay, so what I'd like you to learn as part of this course, or the first part, is we're going to talk about radiation and mechanisms. We're going to go through Fourier's equation. We're going to understand propagation and shielding. We're going to go through things like skin depth, right? We're going to talk about fields in media and antennas. We're going to talk about the speed of light in various media, fields fields at interfaces. We'll talk about Smith charts, matching circuits, and then we'll go through, various characteristics of transceivers, receivers, and then we'll go through some of the basic circuits, including LNAs, power amplifiers, mixers, oscillators, and the like. Okay, so first question: how does an antenna or a system radiate? How do you get a signal from A to B? What's the mechanism? Has anyone gone through this process of understanding if you had an electron in the universe, somewhere in the universe, you have this electron, how you could use that electron in order to convey information? Has anyone gone through that before? Or how you get radiation? Yes? No? Nobody? So what did you guys do first year physics? No, I'm not being rude. I'm just trying to understand. Like, did they do this in first year physics where you've got, okay. All right, so essentially what happens is, if you've got an electron, what can you tell me about an electron other than it has a particular charge? It generates what? Sorry? An electric field, right. Okay. And we know about that electric field. We know that it's Coulomb's law tells us what that electric field is. Now, but if I move that electron with constant velocity, what do I get a change in the Coulomb field? But what do we know about that change in the Coulomb field if I wiggle that electron? If I move that electron with constant velocity, what happens to the electric field? It changes, but it changes as with distance. It changes as 1 on r squared. Right? Why do I care about that? Well, if the field is only changing as 1 on r squared, that means that if you're trying to communicate at the long distances, remember you're going to have the power that you're going to transmit. And I'll go into much more detail about this. Is going to be E cross B, which is electric field, multiplied by the magnetic field. And if the electric field goes as 1 on r squared and the magnetic field goes as 1 on r squared, right? Or even if it goes as 1 on r, their energy is going to go as 1 on r cubed. Which means, what does that mean in terms of distance? Like, for example, if I was trying to send a signal from A to B, how would that signal vary? The power of that signal vary if the power that's only 1 on r cubed. It would be how many dB per decade? It would be 60 dB per decade. So therefore, if you were, 1 meter, it would be whatever. At 10 meters, it would be 60 dB down. At 100 meters, it would be 120 dB down. right? At 1,000 metres, it'd be 180 dB down, and what we'll do at some stage is you'll find that the noise floor is minus 174 dB. You couldn't communicate. So therefore the question is, how can we do something else in order to have an advantage over this 1.5 cubed type of loss, or 1 to the R4 type of loss that we would encounter if we were just moving this electron, or even current, which is the bunch of electrons moving. How can we do this in such a way that we have some advantage? And what happens is, if you go through the mathematics, one of the things that you can convince yourself of is if you actually have this electron, right, and you accelerate it. Everyone knows what acceleration is, right? If you accelerate this electron, what happens is all of a sudden you get this disturbance. And what I've drawn here is, if I can find this, this is the electron. It was at a particular location, and I've accelerated it. So therefore, I've gone from P to P, across this helical line, and I've accelerated. And essentially, what I had was I had the electric field lines, but as part of that acceleration, these field lines are actually being distorted, right? So therefore, initially there was only a radial component. I'll send you all this in the lecture notes, so you don't have to take pictures if you don't need it. It's all going to be in the lecture notes, right? So therefore, you now have this disturbance in the field lines, right? So let's start investigating what this means if we have these disturbances in the field lines. So, if we do some basic trigonometry and we had an electron that was at the location P, and then we quickly accelerated it with some acceleration A and got to the point Q and then went back to constant velocity, what we find is that there's actually a disturbance in the electric field, and there's not only a tangential, but there's not only a radial, there's also a transverse path, right? And if you go through the calculations, what you'll be able to show yourself is that the transverse path disturbance is equal to A times sine theta, and the ratio of the transverse to the radial fields is A times sine theta on C, right? And if you actually go through the mathematics, and you can go through the mathematics, the slides themselves have enough information, is you can actually work out here what the transverse field is. And more importantly, if you go through, what you can actually show is that the transverse field is Q times A sine theta C squared on R. Right? Remember, Coulomb's law goes as 1 on R squared, but the disturbance goes as 1 on R. Right? That is the reason why we can have long distance communications. Because you are now, the electric field, and of course, what you'll find is the magnetic field, decays as 1 on R. Right? If it decayed as 1 on R squared, all of a sudden the distance would be very limited, and wireless communications wouldn't be possible, and you would be living in my era where, I don't know if you've seen the photos in my era, where you had they were on the wall, it was a cable, you put them on, you put them on your ear in order to talk. Whereas this essentially allowed you guys to actually have mobile phones. So, what it's showing, so there's some very important concepts here, right? And the very important concepts are that the transverse field goes as 1 on R, right? And it's also directly proportional to acceleration, right? Now, that's important because what we'll find is that acceleration can be related to, if you had a sinusoidal current. Suppose now let me ask a different question. Suppose I had a particle whose velocity what's its acceleration? Okay. Okay, so so we know, what's this? This is, don't do the calculation, but the x and t is velocity, which is omega cos omega t. All right, and okay. Now, why am I telling you this? You remember all this from your first year differential equations, right? So the point here is that if you know, in the formula here, we've shown that the electric field is proportional to acceleration. And what we can see is if you had an electron in a wire and you were actually wiggling it faster, right, the amount of energy you actually radiate increases proportional to the acceleration, which is also the reason why we also use higher frequencies, higher frequencies had an advantage when the transition from over higher speed. Okay, so, and we've talked about that. Why is this important for communication systems? Okay, now, another important concept. So far, I've been talking about electric fields. And if I'm moving an electron, we know that that electron is, we're going to get a time-varying electric field because we know an electron generates an electric field. If we move that electron, we're going to get a time-varying electric field. Now the question is, how about, do we get a magnetic field? If we're moving an electron, do we get a magnetic field? And let's assume that it was not sinusoidal in this particular case. Do we get a magnetic field? Suppose it was a DC current. Do we get a magnetic field? Does anyone remember Ampere's law? Yeah. So the answer is yes, you do get a magnetic field also, right? Now, the question, however, is, in this particular case, if you're moving it in a particular, because current, right, is, moving the movement of lots of electrons, right? So that's coulombs per second. That's when you say an amp, that's the number of coulombs per second. But anyway, and I'll go through Ampere's law and all the Maxwell's equations in the next slide. But the point here is, Ampere's law is essentially, if you've got a time-varying flux. So remember, have you guys done electric motors and all that kind of stuff? No? Yes? Okay. So remember, if you've got an electric motor and you want to generate power, what you do is you've got a coil and you move that coil, right, in order to cut flux, and that flux actually generates a voltage, which actually is what actually generates the flow of current, right? So here, Ampere's law actually tells us that there's a relationship between magnetic field and the rate of change of flux, right? And don't worry too much about this. The only point that I'm trying to make here, which I think is important, and it's just trying to, for you guys to internalize it, to try to understand and appreciate, is that if you've got an electron which is wiggling around, not only is it producing an electric field and a time-varying electric field and a time-varying disturbance, electric field disturbance, it's also doing the same for the magnetic field, right? And as a consequence, what you're able to do is, if you go through this process, when you're actually wiggling around this electron, one of the advantages is that not only are you generating an electric field, but also a disturbance disturbance in the electric field, and furthermore, what you're able to show, if you go through the calculations, is that actually there's a relationship between the transverse electric field that you've generated to the magnetic field. Now, everyone knows what the speed of light is, right? You've all gone through that. Does anyone know what mu naught E naught is? Permittivity, permeability of a material. Who knows what a capacitor is? Okay. I mean, I find it hard to believe that you don't know what a capacitor is. So you guys must not be putting your hand up, right? Is that correct, or you're? Or do I need to specifically ask people questions? So who doesn't know what a capacitor is? Okay, all right. So you know what a capacitor is, right? So therefore, the property of that dielectric material, which is how easily can you polarize that material and what is the implication of that charge, relates to the relativity of that particular material, which is essentially how well can you polarize that particular material once you apply an electric field to it. And what this equation is showing us is that if you've got an electron and you're wiggling it around, you get a disturbance in the electric field, you get a disturbance in the magnetic field, and what we'll show is once we go into the next few lectures, when we're actually calculating the pointing vector, one of the things that we're able to do is work out how much power we're able to dissipate or actually be able to transmit as a consequence of that. Okay. Now, an example, and I know that you all love examples, right? Suppose who knows how an X-ray source works? Has anyone seen how an X-ray source works? All right, who's not had an X-ray? You've never had an X-ray? All right, lucky you. So everyone, okay. How does an X-ray work? Number 36. I've got to, that's you. That's okay. It's okay. All right. If you don't know, it's okay. Just say, I don't know. Ask. Okay. So essentially, the way that an X-ray source works is you've got a hot filament. Right. Usually, it's a tungsten filament that you put current through. And essentially, what happens is electrons boil off it. Right. So they become free, especially if you think they boil off it. And then what you're able to do is you put a large field, right, between two parallel plates, between where the electrons are coming out and, you know, the other side. And essentially what happens is those electrons accelerate in that field. And, I mean, you can think of the situation that accelerates. So the generating EM radiation may not just be high, but you can actually, as we said, we can actually work out what that is based on how fast they're accelerating. And you should be able to do that based on your understanding of tertiary physics. But then all of a sudden, they move and they smash, you get them to smash into a wall. And you get them to smash into a piece of metal very, very quickly. Right? So you get a massive deceleration. And if you go through that process, that calculation, you can actually work out what is the electric field and also the magnetic field that each one of those electrons will generate as the process of smashing into that wall. Right? And the higher the initial velocity and the faster you can accelerate, the higher the energy of that electron. So that's what I'm trying to do here, is actually show you the calculation where what we're doing is using the equations that we've generated in the previous segment in order to work out what the electric field is that's going to be generated, and of course the magnetic field. Okay, now to the fun bit, Maxwell's equations. All right. Now seriously, who has not heard about Maxwell's equations? Put up your hand, because I know that everyone if I say who has heard about Maxwell's equations, no one puts up their hand. And if I say who has not, maybe I'll have a little bit more success. Who has not heard about Maxwell's equations? Fantastic. So you all know about Maxwell's equations, so I don't have to go through them. Okay. So we'll go from the bottom up. Okay. So let's go through the third one. So specifically, I'm talking about this one, right? So you've got div of d, which is there's a relationship between the displacement field and rho being the charge. You've probably seen this in your first year physics as written in integral form rather than differential form, right? Have you seen that? Gauss's equation. There's some constants missing, right? So therefore there's a epsilon 1 and epsilon naught. Who has not seen that? Perfect, you've seen it. Good. All right. So essentially, and this is in differential form, but what's that equation stating? Can someone say that to me in words, right? Rather than me writing this down, right? Which, if you look at it, you might not mean a lot to you. What I want, and I'm sure you've seen it, but I want to hear someone succinctly describe what that equation is saying. Yes?
It's the total electric field on a closed surface equal to the total charge inside the surface.
Perfect. Perfect. That's what it's exactly saying. And essentially, what the way that it's describing is the electric field flux, which is cutting a surface, is equal to the amount of charge that is encapsulated or enclosed in that surface. Perfect. All right. Equation number one of Maxwell's equations known, Gauss's law for electric charge. How about number two? Okay, if I did this differently, if I wrote it in that's what it's saying, right? I'll ask you, number 28. No, that's okay. Do you know what that means? No? That's okay. I mean, that's fine. We're okay, who wants to... Yes? Right. Yes, exactly right. And what does that mean? Well, why is it significant or important to the physics? Yes, that's what the equation's saying. But what does the physics feel? Okay, so we know we're going to have an electron, right? And that's a point charge. Can we have a magnetic monopole? Can you have a magnet which is only a north pole and no south pole? So that's essentially what that thing's saying. It's saying that they have to come in pairs, and if you've got a surface enclosing the flux, the magnetic flux coming in the surface is, the north and south pole are equal. So if you've got a surface like this, it's always, because you don't have a monopole, the amount of magnetic flux coming into a surface is equal to the amount that's leaving the surface. Great. All right. All right, number one. What's number one? Equation number one. And you've seen this also before. How about if I wrote it like this? Where's that move? can tell me what that equation is called? And this is the generalization of that equation. Who knows who Faraday is? All right, let me just, okay, number 102, right? Yes. Tell me about Faraday's equation. That's you, yes? You're looking at it. All right, what's Faraday's equation? Sure. It's trying to oppose the change in the field. Okay. So this is Faraday's law, which is essentially as the rate of change of flux actually gives you a voltage, right? And that's how you generate power. You know, if you're on a bike and you've got an electric motor, you're actually cutting flux, so you actually have a rate of change of flux, which is actually what gives you a voltage or an electromagnetic force, which actually generates a current. Or so essentially, that's what that equation is showing, equation number 1. It's just Faraday's equation, right? And it's just written in a more general form for Maxwell's equations. Okay, now, all right. How about this? Now, here, you're probably all familiar with Ampere's law, right? You're probably all familiar with that, correct? But Maxwell came along and said, well, that's half the story. Can anyone tell me where this becomes significant or important? Right, so you can think about it, all this is saying is, so, you know, curl of H is equal to J, which is what you know, right? This is just that. But then all of a sudden, Maxwell's come along and said, hey, wait a sec, guys. There's an issue here, and we got to add another term in here, which is related to the electric field or the displacement. What does that mean? Can anyone give me an intuition about what that the delta dt means? And where does it become significant? Can you give me an example? Yes, that's really good. Who said that? All right, yes. But is it because I've got the capacitor down there, or you know that if there's a capacitor? Sorry? Okay, perfect. Okay, so tell your colleagues that are your shy colleagues, because they don't want to say things, and I'm glad that you shouted, you said this. What's the importance of that being in a capacitor? What does it mean? You're absolutely right, 100% right. Yeah.
No current goes through the
right.
But it will also generate
Perfect. Yeah, yeah. So essentially what it's saying is that you need to also include displacement current, because as the even though you don't have direct flow through that surface, because it might be a dielectric with a very high resistance, what happens is the change in the distribution of charge on either end relates to a displacement current, which is essentially what generates another form of current. So it's not actually direct current, it's also, you need to include the displacement current. And as your colleagues or fellow student has just pointed out, that is what happens when you've got a capacitor, right? So if you had a capacitor and no direct current flows, right, what happens is you're getting a distribution of, and this is supposed to be, you know, time varying, right? As you're varying that voltage, what happens is you're getting a redistribution of current on either plate, in this particular case, which is actually causing currents to flow, right? And that's what the delta dt is supposed to capture. Perfect, right? So now, these magical equations which seem infinitely hard, and I remember being a student and cursing these Maxwell's equations because, you know, lecturers would always put them on the board and say, these are Maxwell's equations, but I never understood what they were. Well, hopefully now you will understand what they actually mean and why they're going to be hopefully useful. All right, now, the thing that I wanted to also go, and this is the last thing that I'll talk about before the end of the lecture, which I think I've got another 10 minutes, is if we had now a couple of parallel plates and we apply a voltage on those parallel plates, what we'll get, of course, is we'll get time-varying electric field, right? So the question is, do we expect to also get a magnetic field? And the answer is yes, right? Maxwell's equation just tells us that, you know, if we go through the whole process, we get, you know, if we've got the electric field, we can actually determine the time-induced electric field, a magnetic field, through this whole process, and we can work it out. But then we know that the magnetic field also generates the rate of change of magnetic field also affects or produces an electric field. And if we go through this process, we actually work out what at least the second order, what the electric field is. Now, can someone tell me, if you're looking at this electric field equation, right, and there's multiple further terms, what's the significance of it? Right, it's a little bit different to what you would expect. Like if you're doing your basic understanding of capacitors, right, you usually have your capacitor and you just say, oh, its impedance is 1 j omega c. And you're like, cool. And then you go get a real capacitor and plug it into a circuit, and it's like, oh, geez. It doesn't really do that. What's this 1 j omega c stuff that, you know, all my lecturers at Melbourne Uni have been doing, you know, put a capacitor in there, it's 1 j omega c. Sorry, it's not that. What's this actually telling us? So if we look at that electric field, and it's a direct consequence of Maxwell's equations, or a direct consequence that an electric field induces a magnetic field, and the magnetic change of magnetic field induces an electric field. What can someone tell me about this capacitor? What can someone tell me about that capacitor? Is the electric field always positive? Always positive. Is there no R in there where the field vanishes? People are waving, nodding, so everyone just want to say, no. So what you see here is there are, you know, frequencies at which this capacitor, the field actually goes to 0. And what you do is if you go through the process, you can actually convince yourself and go through the calculations. What happens in this capacitor is there's a frequency where the field disappears at the end of the capacitor and the magnetic field begins to increase. Now, what does that all mean? Well, if you get a real capacitor, and when you're building chips, or you're building chips at 60 degrees like I've been doing, you find that a lot of times these capacitors aren't real capacitors, right? They've got resistance and they've got inductance, right? And I've just shown you that this particular capacitor has also got an inductance because it has a magnetic essentially what I'm saying is you can't go to DigiKey or whatever, even if you weren't building the inductor yourself, you can't get an inductor that has no ESR and no ESR. Who knows what ESR is? Okay, anyone else? Essentially, when you buy a real capacitor, right, and what it has is it's got series resistance, it's got the capacitance that's written on the label, but it's also got inductance, and that is a fundamental property of the geometry of that capacitor. You can't do anything about it. And what it means is there comes a frequency where that capacitance actually goes to zero, that you identify as the self-resonant frequency of that actual capacitor. And that's a fundamental thing of Maxwell's equations, and you can never beat that. All right, so in the last few minutes, let's go through our review. Okay, what did we learn in our lecture today? Okay, so let's do this full screen. What we learned is accelerated charges radiate. Okay, we learnt that the radiated signal, at least the E and the B fields, vary or decay as 1 on R. Right, the power goes on 1 on R squared, but each of those, the B and the E field go as 1 on R. Right? For this, if you had an electron and you were accelerating it, you find two things, which is the disturbance that you generate is proportional to the acceleration, but it also decays as 1 on R. And also, there's a relationship between the magnetic and electric fields, and in the relationship, they're related between the speed of light, permeability, permittivity of free space. You know, the next one, the acceleration charges are used to produce radiation. Well, that's no big deal. We've gone through Maxwell's equations, and we've worked out, we understood what Faraday's law was. We've gone through Ampere-Maxwell's equation, or law, and we know that the difference between Maxwell's or Ampere's equation and Maxwell's equation is that Maxwell discovered that there's also a displacement current that needs to be taken into account, and that displacement current is important in things like capacitors and the like. We've found or understood Gauss's law, which is the flux lines cutting a surface are proportional to the amount of charge enclosed. And lastly, what we determined or learnt today, or reminded ourselves today, I should say, is that there are no magnetic monopoles. So therefore, the flux, the magnetic flux lines cutting any surface is zero, because the amount of positive flux going into a surface has to equal to the amount that's leaving the surface. And then, of course, we finished off by talking about capacitors, and we talked about that displacement current actually generates not only an electric field, which is what we're used to and think about when we talk about capacitors, but also generates a magnetic field. And what we'll do in the next, not the next lecture, in a few lectures' time, we'll be able to work out what the specific inductance is, the amount of amount of power which is stored in the capacitor. And what we'll also do later on is work out for any arbitrary shape or any arbitrary geometry how to calculate those parameters. And this is a fundamental property. You can't design around it, right? You can actually change the geometry a little bit in order to reduce it, but essentially, if you've got a displacement current, you've got a magnetic field, and you've got to live with it. And it also means that this is something that's absolutely critical because it dictates the self-resonant frequency of the capacitors, which means which dictates what's the maximum frequency you can actually use that capacitor or that particular component in your RF system. And that's it. That's the lecture for today. Questions, abuse, quiet, silence. I'll upload them. don't know if the lecture's recorded or not, but I know the lecture notes are going to be up there. I don't know, I'm sorry. Yeah, absolutely.
Because when we go through the class,
Are you, okay, I'll definitely.
Right, yeah.
Okay, I'll definitely do that.
What
No.
about in the future, all the lectures are those copyrighted or
Handwritten, unfortunately, because I've just started now, because I've been away and I've just started, and this is just the next 2 lectures, right? And there's no way that I can actually type it all up because it's just too much.
So you will put it on LMS, right?
Yeah, I'll put it on LMS. Yeah. And I've also got other reading materials I'll put on there and all that kind of stuff.
Thank you.
They're going to be. I haven't put them on there. I will put them on LMS. Okay, let me see what I can do. Because sometimes I'll be producing the lecture notes the morning before, right? But I'll try. Okay.
Sorry, I sent you an email, was it 2 days ago, I think, or yesterday, because I had some issues with my enrollment application.
But I think I responded.
Exactly, yeah.
Okay,
So, yeah,
perfect.
thank you very much for that.
Okay.
I'm just going to sort everything out tonight and it should be fine for next week.
Perfect.
And, just wondering, do you know right now the workshop, like, what less time stuff?
I don't. It's on the how do you call it, on the
Yeah, timetable.
on the timetable. Yeah.
Because I just know that in some subjects, like, they have a lot of full slots and then not all of them are like full slots. Yeah. Like, I'm not...
So yeah, just find out. The problem is, I've been away for a few years. So everything's changed, and so it's both of us. You know, I'm learning how to do put all the stuff online, and use all their systems. But before the end of the lecture, I'll have it all sorted out. I'm sure.
Yeah, thanks very much.
Okay, no worries.
The two kinds of two types of lecture notes in the LMS.
No, they're going to be new ones. I'm putting my ones. Don't put the old ones.
Both of them are old.
Yes.
Logic and R.
Yeah.
So all the lecture notes in LMS is the old one.
Yes. I haven't put in my new ones yet. No.
Is that looks similar? I mean, the old lecture.
No, they're going to be very different.
Very different.
Very different.
So what's this lecture talking about? Because like it's very different, so I don't know any direction about it.
Yeah, but I told you what we're going to do, right?
Yeah,
Okay. So it's very different in the sense that some of the concepts are the same, right? But what I want you to learn is no. Maxwell's equation is just a start, right? So you learn Maxwell's equation, but what I want you to know is understanding radiation, right? Now next lecture we're going to talk about propagation and shielding, right? So you're going to work out about skin depth. You're going to work out what happens in fields in media. Then after that, I'll go through antennas, and I'll actually go through vector magnetic potentials. I'll talk about pointing vectors. You'll learn how to the radiation from a dipole, from a small dipole to various dipole. You'll learn about radiation resistance, all that kind of stuff that you need to. If you're going to be an RF engineer, or if you're going to be anyone that's designing any electronics, you need to know about this. The past lectures don't have any of that. So that's why I wish they did, because then all I would have done is I wouldn't have to write them. I'd just copy them. Right? So I'm going to make it a little bit different. Now, some of the Smith's charts and matching is the same. Basic matching circuits is probably going to be similar. This is all different. I'm going to go into much more detail on how to design LNAs, PA,